Hello everyone, this is Safa and welcome back. In this video, we will design and analyze a lag compensator in MATLAB. We will start with an original plant and its closed loop system. Then we will design a lag compensator and connect it to the plant. After that, we will compare the original and compensated systems using step responses, Bode plots, pole zero maps, and steady state error. First, here, we'll start by clearing the MATLAB environment. CLC clears the command window. Clear removes variables from the workspace, and close all. Closes all open figure windows. This gives us a clean environment before starting the simulation. Now here, we define the original plant. The numerator is defined as num equals 1. And the numerator is then equals 1, 2, 1. These coefficients represent the transfer function 1 over s squared plus 2s plus 1. And next, we use the tf command to create a transfer function model. We store this model in the variable g. And finally, we display the original plant in the command window. Okay, next we create the original closed loop system. The feedback command is used to create a unity feedback system. Here G is the forward transfer function and 1 represents unity feedback. The resulting closed loop transfer function is stored in T. And we here display the closed loop system in the command window. Okay. Here we are ready to analyze the original closed loop system. First, we create a new figure window. The step command plots the step response of the closed loop system T. Grid on adds a grid to the plot, and then we add a title and label the horizontal and vertical axis. At this stage, we are only analyzing the original system. We will compare it with the compensated system later. Now we define the lag compensator. The numerator coefficients are 10 and 10. The denominator coefficients are 10 and 1. Therefore, MATLAB creates the compensator transfer function using the tf command. We store the compensator in the variable gc. Finally, we display the compensator in the command window. Notice that the compensator has a pole closer to the origin than its 0. This is the characteristic structure of a lag compensator. Now we connect the lag compensator to the original plant. We use the series command. The series command connects two systems in series. So here the compensator GC is connected in series with the plant G. The resulting compensated open loop system is stored in L new. We then display the transfer function in the command window. Okay, the next step is to close the feedback loop. We again use the feedback command. The compensated open loop system LNew is connected with unity feedback. The resulting closed loop system is stored in T_new. This is the system that we will use for the final comparison with the original closed loop system. And here we compare the step responses of the two closed loop systems. The original system is plotted in blue. The lag compensated is plotted in red. The legend identifies the two curves. This plot allows us to directly compare the transient and steady state behavior of the systems. We will analyze the actual response after running the complete code. Okay, here we compare the frequency responses. The Bode command generates the magnitude and phase plots. Here we compare the original open loop plan G with the compensated open loop system L new. The original system is shown in blue. And the lag compensated system is shown in red. Okay, the Bode plot helps us see how the compensator changes the frequency domain behavior of the system. Okay, here we examine the pole zero location of both closed loop systems. We create a new figure and divide it into two subplots. The first subplot shows the poles and zero of the original closed loop system, and the second subplot shows the poles and zeros of the lag compensated closed loop system. Pole locations are particularly important because they determine the stability and dynamic behavior of a control system. Again, we will examine the actual locations after running the complete code. Finally, we calculate the step response characteristic. The step info command provides important time domain characteristic. These include rise time, settling time, overshoot, peak value, and peak time. First, we calculate this characteristic for the original closed loop system, and then we calculate the same parameters for the lag compensated system. This will allows us to make a quantitative comparison between the two systems. And here, the last part of our code is the steady state analysis. We use the DC again, here you can see, command to calculate the final value of each closed loop system. The final value of the original system is stored in, here you can see original final value. The final value of the compensated system is stored in compensated final value. For a unit step input, the steady state error can be calculated as the absolute difference between 1 and the final value. Therefore, we calculate the steady state error for both systems. And finally, we display all of the steady state result in the command window. We display the original final value, the compensated final value, the original steady state error, and the compensated steady state error. Now, the entire code has been explained. Instead of running each section separately, let's run complete script and analyze the result. Okay, run. Okay, here first in command window. Okay. MATLAB first shows the original plant. The transfer function is 1 over s squared plus 2s plus 1. And after applying unity feedback, the closed loop transfer function becomes 1 over s squared plus 2s plus 2. This is the system we use as our original closed loop reference. And then MATLAB now shows our lag compensator. We can see that the compensator introduces an additional pole and 0 into the system. After connecting the compensator and the plant in series, the system becomes a third order open loop system. After closing the feedback loop, we obtain the final compensated closed loop system. This is the system that we compare against the original closed loop system. Okay, and here we can see original system and compensated, lag compensated. Okay, now let's compare the step responses characteristic. The original system has a rise time of about 1.52 seconds and a settling time something about 4.22 seconds. It's overshoot. It's approximately 4.232%. After adding the lag compensator, the rise time become okay, here rise time 1.61. However, the settling time increases to approximately 7.32 seconds. The overshoot also increases to about 40.44%. So, in this particular example, the lag compensator does not improve the transient response. Instead, its main benefit can be seen in the steady state behavior. Okay. Here, now let's look at the step response compression. The blue curve, okay, here you can see. Blue curve represent the original system, and the red curves represent the lag compensated system. Okay, the red curve, we can see the compensated systems, red one, reaches as much higher final value. However, its transient response is different, with more overshoot and a longer settling time. This is an important point. A compensator should not be judged only from one performance measure. We need to consider both transient and steady state behavior. Okay, and next here, Bode plot. The blue curve represent the original open loop system, while the red curves represent the lag compensated system. The compensator changes the magnitude and phase characteristic of the system, especially at lower and intermediate frequencies. This frequency domain change is related to the steady state performance improvement we observed in the time domain response. And okay, finally, let's look at the pole zero maps. Okay, the left plot shows the original closed loop system. The right plot shows the lag compensated closed loop system. The compensated system has additional poles and zeros because of the lag compensator. All of the closed loop poles remain in the left half of the S-plane, so the system remains stable. However, the pole locations are changed, which explain the change in the transient response. Okay, here we reach the most important result of this example. Okay, in command window. Here, okay. The original system has a final value of 0.5. Therefore, for unit step input, its steady state error is 0.5. After adding the lag compensator, the final value increases to approximately 0.9091. As a result, the steady state error decreases to approximately 0.0909. So the steady state error is significantly reduced. This demonstrates the main purpose of the lag compensator in this example: improving a steady state accuracy while accepting some changes in transient performance. Okay, in this video we designed a lag compensator in MATLAB and analyzed its effect on the closed loop control system. We first modeled the original plant and closed loop system, then we designed the lag compensator and obtained the compensated system. We compared the system using step responses, Bode plots, and pole zero maps. Finally, we compared their steady-state errors. The original system had a steady-state error of 0.5, while the compensated system reduced this error to approximately 0.0909. However, this improvement came with a slower settling response and increased overshoot in this particular example. This shows an important principle in control engineering. Improving one performance characteristic can affect other characteristics. In the next lesson, we can move to another important compensator design technique and continue building our understanding of classical control design in MATLAB. Thanks for watching.